Topic of today, I want to give you a little overview of this unit. Some teachers call this unit polynomials. I like to call it factors and products and it's factors and products essentially of polynomials because it really describes the process that we're going through. Okay, so factors and products, what does that mean? Well, let's start out with numbers. Okay. If you're finding a product, what are you figuring out? Yeah. Answer for multiplication. So if I do 2 times 3 equals 6. Okay. Going in this direction means I'm finding a product. What if I go in this direction? Take the 6 and I break it up into 2 times 3. Yeah, you're factoring. Yes. Okay. So you guys have been doing multiplication for a very long time. You're familiar with it. We're going to be doing it with algebraic expressions. Okay, we're going to be taking 2 algebraic expressions and we're going to multiply them together perhaps. And then we will also go in the opposite direction. So in grade 9, you guys would have, or hopefully, if you didn't, I know that there were some gaps because of, the past 2 years, but you would have looked at some finding a product. When you're doing it algebraically, often it's called expanding. You probably haven't looked at factoring yet in terms of algebraic expressions. Okay, so we're going to look at both. Factoring specifically of polynomials is an incredibly important skill that it's important to be fluent in because it will continue in every level of math that you do going forward. Okay, much more so in the pre-calculus streams, which is the -1 stream, but also in the -2 stream as well. Okay, it's a very important skill. Okay, so another thing that I want to just show you as an overview is that multiplication can be modeled through the area of a rectangle, right? So if I'm looking at 2 times 3 equals 6, I can model that visually by looking at a rectangle that is 2 by 3, and the area is 6. Okay. Now, we are going to be using similar models when we look at factoring and expanding algebraic expressions. Okay. This is a pretty simple one, but you can also use this area model, and some of you guys may have seen this before, for more challenging multiplications, right? So I just want to show you guys because this directly translates to what we're going to be doing algebraically. If you did something like this, 34 times 27, does that look familiar to you guys? Would you know how to multiply those 2 numbers together? Yeah? Okay. So where do I start? What do I do first? Yep.
You multiply what's in the ones first. So you
Yeah.
apply 7 to the 4, and then 7, so you apply 7 to the 4 up there.
Yep. 28.
Above the tens column there.
Okay. Yeah, so 7 times 4 is 28. So I have 8 ones and 2 tens. The 2 tens goes over there because this is the tens column. And then what? Well, no. Anyway, yeah. Okay, so 7 times 3 is 21. Add the 2 is 23. So I write that down. And essentially, I have 23 tens, which is 230, which is why those numbers are in those specific place values, right? Okay, now what? You add a 0, yeah, okay. Yep. Okay, yeah, that's not a bad idea. Erase the 2, okay. Yeah, then what?
2 times 4.
So you go 2 times 4, yeah, is 8, right?
2 times 3 is 6.
And then what? Then you add. Okay, so this is 8, this is 11. Yeah, so it's actually not 11, it's 11 tens, right? Which is 110. So I have a 1 in the tens position and a 1 in the hundreds position to represent 110. okay? And then I add these ones, right? So that's what, 918. Okay, we're all familiar, we feel comfortable with that? Okay, so another model that you can do that I think actually shows the process much more clearly is using an area model, okay? So I'm going to make a rectangle that's 34 by 27. Not very nice to multiply by 34 and 27 though. So I can break those numbers up into a sum. I could break 34 into a sum of two numbers where both of those numbers are easy to multiply by. If I broke 34 into something plus something, where I want those two things to be really easy to multiply by, how would you break it down? Yeah.
Maybe divide it by 2 or something?
Well, if I divide it by 2, then I'm going to have 17. So I could, but I'm not sure if 17 is easier to work with, 17 and 17, than 34. Any ideas? What about doing it this way? 30 and 4. Those ones are pretty easy to multiply by. Okay, and this way, how would you break down the 27? 20 and 7, yeah. Okay, now this piece of the rectangle, I've essentially divided the rectangle into 4 sections. This piece represents 20 times 30. How much is 20 times 30? Yep, 600. This piece represents 30 times 7. How much is that? Yep, 30 times 7. Yeah? I heard someone say it. 210, yeah, because 3 times 7 is 21, so 30 times 7 is 210. And then this piece represents 20 times 4, which is 80. And this piece represents 7 times 4, which is 28. So all together, it's going to be 600 plus 210 plus 80 plus 28. Okay, so this is what? 108, 318, 918. So we can do this with numbers. We're going to be doing something similar with algebraic expressions, and that's kind of where we're going. Okay? All right, now, let's get on to what we're talking about today, because this is really, the other thing, by the way, that we're going to be doing is taking this product, 918, and using some sort of model that looks like this to break it down into, oh, that's 30 plus 4 times 20 plus 7. Okay, not with numbers, but with algebraic expressions. Okay, that's an overview of the whole unit, though. Let's talk about what we're going to do today. Today we're going to talk about greatest common factor and least common multiple. Okay, you guys have seen these concepts before, particularly with numbers. But we're going to learn a new method that you can use to find the greatest common factor or least common multiple of several numbers or perhaps several algebraic expressions, okay? Because that's going to be an important skill when we try and factor or we try and find a product perhaps, okay? So I'm going to really rush through these definitions because in fact we already discussed this when we were simplifying radicals. Sorry, I'm getting a call. I have to answer a text quickly to tell my husband that I did not feed the dogs this morning. No, I didn't. There we go. All right. Otherwise, he's going to keep calling me and calling me. Okay, so factor. A factor is a number that divides evenly into another number. Right? So for example, 2 is a factor of 10 since 10 divided by 2 equals 5. Yep?
By number, does it have to be like an integer? Or
Yes, good question. It does have to be a whole, well, in fact, specifically, I would say a natural number when we're talking about multiplication. Yeah. Okay. So you can't say, for example, that 4 is a factor of 10, even though 4 times 2.5 is 10. A factor, when you divide by it, you have to get a whole number. Good question. Okay. Prime number. Prime number is a number with exactly 2 factors, right? And the 2 factors would be 1 and the number itself. So we saw a lot of this already, stuff like 2, 3, 5, 7, 11, 13, etc. And there are infinitely many primes. It's actually quite hard to prove that. I spent like, I don't know, half a semester in university trying to look at specifically that proof. But it is true that there are infinitely many prime numbers. Okay? Composite number. Composite number has 3 or more factors. So it has to have a factor of something other than 1 or itself. Okay? So for example, like 10 is composite because 10 has 4 factors, 1 and 10 and 2 and 5. Yes?
9 with
Yeah.
number because we divided by 3.
Correct. Yeah. 9 is composite. Yeah. 9 has 3 factors, 1 and 9 and 3. Yeah. And do you guys know the one number that doesn't fit into any of these categories? Yep. 1. 1 only has 1 factor, right? So it doesn't have exactly 2, and it doesn't have 3 or more. So 1 is sort of in a set all by itself, okay? 1 is the loneliest number, they say. All right, so prime factorization, we already know what this is. It's the process of breaking a composite number up into the product of primes, right? So if I wanted to look at the prime factorization of 10, we did this either using a tree or a ladder. With this one, probably most of you can do it in your head. 10 is 2 times 5. Okay? So I'm going to skip through this quite quickly because we've done so much with prime factorization already. But if I wanted to write out the prime factorization of 3,300, then essentially what I want to do is start breaking this down into the product of other numbers that are smaller. It doesn't have to start to be prime. If you're using the ladder model, then that's what you're going to want to do. So this is even, so I can divide it by 2, and I believe I get 1,650. And I can break that down again, divide that by 2, and I get 825. And I wouldn't expect you to do this in your head. You can use a calculator. I can divide this by 3, and I'm going to get, what is it, 33? Is that it? Can someone check that? No, it's not 33. What am I saying? Thank you. Where am I getting 33 from? Okay. This is not divisible by 3. Do you know how I know it's divisible by 3? Have I talked about that? Yeah. Yeah, you add the sum of the digits has to be divisible by 3 as well. So this adds up to 15, so I know that's divisible by 3. This adds up to 14, so it's not. Okay. This is divisible by 5, though. And when I divide that by 5, what do I get? 55? Thank you. And then I can divide that by 5 again, and I get 11. Okay? So the prime factorization, if I ask you to write out the prime factorization of this number, and you just give me that, that's not actually the prime factorization. The prime factorization is this. 2 times 2 times 3 times 5 times 5 times 11. Okay, again, I have written the primes in order from least to greatest, but you don't have to do that. What you'll find, though, probably after this lesson is we're going to be doing a lot of comparisons of different prime factorizations. So it's helpful when you're comparing to have it organized. Yeah?
Is it proper to add exponents to it? Can you do like 2 squared?
You can do either. Yes, absolutely. I was about to get to that. Or you can write the repeated primes using exponents, right? So instead of 2 times 2, 2 squared, times 3 times 5 squared times 11. Okay? All right, greatest common factor. If I asked you for the greatest common factor of, let's say, 18 and 45. What does that mean? What number am I looking for? Yeah. Okay, it would be 9. Yes, that's correct. How would you describe it, though, in general? Yeah?
The number or the number that has the highest value that divides evenly.
Yeah, exactly. So it's the largest factor that both numbers share. Okay? So one strategy, I mean, many of you guys can do this one in your head, but I believe when you were younger, what you may have been taught is we'll write out all of the factors of 18, write out all the factors of 45, and then compare, right? So for example, if we're looking at the factors of 18, I always start at the end, at the extreme and work inwards. So what I mean by start at the extreme is start with 1. 1 and 18 are factors, right? And I don't know, I was always taught, oh wait, did it backwards. I was always taught to do it this way where you like leave space in between so that you could put them in order. Some of you guys may have seen that before. Okay, is 2 a factor of 18? Yep, so 2 works, and 2 times 9 is 18. Okay, and then what about 3? Yep, 3 works, and it's 3 times 6. What about 4? Nope. 5, nope. 6 is already on the list, so you're done. You've exhausted the list, okay? Then if we look at 45, we've got 1 and 45. Does 2 work? Nope. Does 3 work? Yep. It's 3 and 15. 4. Nope. 5. Yes, 5 times 9. 6. No. 7, no. 8, no. And in fact, if 2 doesn't work, none of the even factors will work. Okay? And now we're at 9, so the list is done. Okay? Now we compare and we see that that's the largest one. It's not the only one. They also have a common factor of 3, and of 1, of course, but it's the largest common factor. Okay? And you guys have been familiar with this for a really long time. Where this has come up quite a bit is in reducing fractions, right? So if I gave you like 18 over 45, that's where you would use this, because you would say, okay, well, I want to take out the greatest common factor of each of the numerator and denominator. So I can write 18 as 9 times 2 and 45 as 9 times 5. And then these cancel. So this is probably where this has come up quite a bit so far. Okay? All right. Now, writing out lists is fine if the number doesn't have too many factors, or if it's really easy to identify the factors in the number. But it can be really tedious and difficult if you're dealing with a very, very large number or several large numbers. Okay, so there's another strategy that we can use, and the strategy that we can use is by looking at the prime factorizations of each of the numbers and comparing the primes in their prime factorizations. Okay, so here's another method, and this is the one that we're going to use. Is to use prime factorization. Okay, so if I look at the prime factorization of 18, right, it's 2 times 9, 3 times 3. And if I look at the prime factorization of 45, not divisible by 2, but I can do 3 times 15, and then 3 times 5. Okay, so what I'm going to do is I'm going to write out 18, or the prime factorization of 18, I should say, and I'm also going to write out the prime factorization of 45, equals 3 times 3 times 5. Okay, and the greatest common factor is all of the primes that they share in their prime factorization. Okay, so the GCF is the product of all shared primes in the prime factorizations. Okay, so when I'm looking at this, what I do is I just start with the first one, and I underline the shared primes, right? So I say, okay, this one has a 2 in it. Does this one have a 2 in it? No, so that's not shared. I can't put that in my greatest common factor, okay? This one has a 3 in it. Does the other one have a 3 in it? Yeah, so that's shared. This has another 3 in it. Does this one have another 3 in it? Yep, so that's also shared. And then once you get to the end of one number, you're done, because you've run out of numbers to compare it to, right? So even if this has a 5 in it, because I've already looked at this one, it doesn't have a 5 in it, otherwise I'd already have underlined it. So the GCF is 3 times 3, which is 9. Okay, and this is a really efficient method, and it also works for algebraic expressions when you're looking at the greatest common factor of algebraic expressions. The prime factorization of algebraic expressions, you can't exactly prime factorize those, but there's a similar process, okay, which we'll get to not tomorrow, on Monday. No, not Monday. I can't remember. Sometime next week. Okay, so determine the greatest common factor of 138 and 198. Okay, so what we're going to do is look at the prime factorizations of each of those, right? So if I'm looking at 138, let's fix that. Okay. Well, this is divisible by 2, so I can start with that. And I am going to get 69, I believe. No. Yeah. Because 140 divided by 2 would be 70. So this is 69. Okay. Can I divide by 2 again? No. Can I divide by 3? Yes. Whoops. And 69 divided by 3 is 23. Okay. Do I need to keep going? No. 23 is prime. Okay. So now I'm going to look at 198. And I can divide that by 2. And I get 99. And then I can divide that by 3. And I get 33. And then I can divide that by 3, and I get 11. Okay? So when I'm writing out the prime factorizations, 138 is 2 times 3 times 23. And 138 is 2 times 3 times 23. 198 is 2 times 3 times 3 times 11. And then when I'm trying to find the prime factorizations, I'm going to compare and ask myself, what are the primes that they share? Okay, so I'll start with the first one, just because. I could start with the second one if I wanted to. Do they both have a 2? Yeah. Do they both have a 3? Yes. Do they both have a 23? No. So you're done. That's it. The GCF is 2 times 3, which is 6. Okay? All right. So what I want you guys to do is to try this one yourself. And then we're going to talk about least common multiple. I want you to use prime factorization to figure out the GCF of 126 and 144. So it seems like you guys have gotten the hang of that. Let's talk about least common multiple, okay? What are multiples of a number? Multiples of 4. Yeah.
They're the numbers that multiply with one another that create the product, I guess you could say.
Okay. So multiples of 4, for example?
Or 2 and 2.
No, not 2 and 2. Those are the factors. What are multiples of 4? Yeah.
4, 8, 12.
Yes, 4, 8, 12, 16, etc. So when you were in elementary school, I know my kids are in elementary school right now, they call this skip counting. You heard of that? Skip counting by 5s is 5, 10, 15, 20, etc. So you can think of it that way, but a multiple of a number is essentially a copy of a number. So if 5 is a multiple, 20 is a multiple of 5 because it's 4 copies of 5. Does that make sense? Whoops, let's switch to black. What's going on with my spelling today? Okay. Copies. So multiples are copies of a number, right? So for example, 20 is a multiple of 5 since it's 4 copies of 5. Okay? Least common multiple between several numbers. So let's say I'm looking for the least common multiple of, I have an idea. Well, no, that's going to be, let's do it. I was going to say 18 and 45, because that's what we did for the greatest common factor, right? Least common multiple of 18 and 45. And this is probably one that's a little harder to do in your head, okay? If you don't know what it is, if I said what's the least common multiple of, 3 and 4, do you guys know what that is? It's the least common multiple of 3 and 4? 12, right? Least common multiple, by the way, is if you're looking at finding a least common denominator between several denominators, that would be the least common multiple of those denominators. So that's where least common multiple has probably come up for the mostly so far, okay? So yeah, so if you have 3 and 4, the least common multiple would be 12, okay? What if you have 10 and 15? What's the least common multiple there? 30, yeah. Okay, so something's going on there though, because when it was 3 and 4, the least common multiple was 3 times 4, which is 12. When it was 15 and 10, that's what I said, right? The least common multiple is not 15 times 10, which is 150. It's a much smaller number. So we have to actually understand why and come up with a systematic method of figuring out the least common multiple. Now, if you don't know what this is yet, I'm guessing probably most of you don't. How would you take steps to figure out what the least common multiple of 18 and 45 is? Yeah. Yeah, write out a bunch of multiples. 18, 36, 54, 72, 90. Is that it? 108, 126, 144, etc. Okay? Is that right? Yeah. Did I miss something? Okay. Yeah, no, I think we're good. Okay. This one's wrong. Is that one wrong? 118. No, that's right. Plus 18 is 126? Yeah, okay. Whew. All right, 45. So 45, 90, 135, 180, 225, etc. Okay, yeah. Yeah, go ahead. No? Okay, so what's the least common multiple? 90. It's not the only common multiple. A multiple of 90 would actually be another common multiple. So 180 is another common multiple, but 90 is the least common multiple, right? So again, if the numbers are relatively small, writing out lists of multiples and comparing is not too tedious. But when they get much bigger, it becomes not such a fun process, right? So let's look at how we could figure this out through prime factorization. Now we've already prime factorized 18 and 45 because we did it when we were finding the greatest common factor. So using prime factorization, okay, we already know that 18 is 2 times 3 times 3, and 45 is 3 times 3 times 5. We did that a few minutes ago. Okay, now here's the key. In the greatest common factor, least common multiple. In the least common multiples prime factorization, you have to be able to see the prime factorization of each of these individual numbers. So somewhere in that prime factorization, I have to have a 2 times 3 times 3, and I have to have a 3 times 3 times 5. But if they share any primes, I don't have to repeat them. Okay? So what I mean by that is this. Least common multiple must contain both prime factorizations, but no need to repeat if they're shared. Okay, so how am I going to start? Well, if it has to contain both factorizations, it must have a 2 times 3 times 3 in it, because that's the prime factorization of 18. So I'm going to start with that. Okay. Now, if I move on to the 45, it must have a 3 times 3 times 5 in it. Do I have any of those covered yet? Yeah, which ones are already covered? Which ones do I already have in there? Yeah, the 3 times 3. I've already got the 3 times 3. The only prime that I'm missing from 45 is the 5. So I have to add that in. Okay, so I don't have to repeat them if they're shared, but I have to make sure that I've got everything covered. Now what you can see is this piece is 18, and this piece is 45. Does that make sense? Kind of? Okay. And then, of course, I would expect that you would evaluate that, right? So when I mean evaluate it, what is the value of 2 times 3 times 3 times 5? And it is, we already know because we figured it out this way, that would be 90. Okay? Question so far? No? All right, so let's try another one of these. Determine the greatest common factor and the least common multiple of these numbers. Okay, so for both cases, I need to start with the prime factorization, right? So that's what I'm going to start out with. So if I'm looking at 140, then I can divide that by 2. And that's 2 times 70. I can divide that by 2 again. That's 2 times 35. And then this I can divide by 5. 5 times 7. Okay, and then if I look at 120, this is divisible by 2, and that's 60. And I can keep going with the 2's. 60 divided by 2 is 30. 30 divided by 2 is 15. And then this is not divisible by 2 anymore, but I can divide it by 3. It's 3 times 5. 5 is prime, so I can stop. Okay, and then finally, 300 is also even, so I can divide that by 2 and I get 150. And I can divide that by 2 and I get 75. And 75 is divisible by 3. It's 3 times 25. And then this is 5 times 5. Okay? So, and this is why I mentioned when we were first talking about prime factorization, it's helpful to write them from least to greatest, because here we need to compare, right? And if it's organized, it's easier to compare. So 140 is 2 times 2 times 5 times 7. 120 is 2 times 2 times 2 times 3 times 5. And 300 is 2 times 2 times 3 times 5 times 5. Okay, so for my greatest common factor, what I'm going to do is I'm going to underline all of the shared primes. So I'm just going to start with the first one. You could pick any one to start with to start your comparison. All right, so let's start with 140. Do all of the prime factorizations have a 2? Yes. And I like to underline all of them so I know I've used that one up. Okay, do they all have a second 2? Yes. Okay, do they all have a 5? Yep. Do they all have a 7? No. So this is my greatest common factor. Okay, so the GCF is 2 times 2 times 5, which is 20. For my least common multiple, let's change that. LCM. To look at my settings so I can make the standard thickness the thinnest one. Okay, so for my LCM, what I'm going to do is I'm going to start by writing out the prime factorization of one of them, because I have to have that in there. So I'm just going to start with 140, right? So it's 2 times 2 times 5 times 7. Okay, so that's got to be in there. That's the 140 piece. Now I'm going to move on to the 120, and I'm going to say, okay, I need 3 2s, a 3, and a 5. Am I missing anything from here that I need to add in to take care of my 120? Yep. A 2 and a 3, because I have 2 2s, but I need 3 2s. So I need to add in another 2. And I don't have any 3s, so I need to add that in as well. Do I have the 5? Yes. Got the 5. I don't need to repeat that. Okay? Now I'm going to look at the 300, and I'm going to see if I'm missing anything there. So I need 2 2s. Have I got 2 2s? Yes. Have I got a 3? Yes. Have I got a 5? Yep. Have I got a second 5? No. So I'm going to add that in. And now I have the prime factorizations of each of the 3 numbers considered in the prime factorization of my least common multiple. Okay? Now I need to multiply this all out. So I don't know what that is. It's 4,200. Thank you. Okay? It would be really annoying to have to write multiples of each of these numbers up to 4,200. It would take a really long time. Okay? All right, so I want you guys to try this one using the prime factorization. Side length of the smallest square that could be tiled with rectangles that measure 16 by 40, 16 centimeters by 40 centimeters. Assume the rectangles cannot be cut. Sketch the squares and the rectangles. Okay, so I've given you a diagram, but I don't have to for this question, okay? So essentially what we're doing is we've got these rectangular tiles. We want to make them into a square. Okay, so we're going to lay them down. Lay down, if you will, copies of the tile. in two directions so that if it's a square, the length and the width are exactly the same. What do we need to find between these two numbers to determine that the size of that square? Yep. The least common multiple. Yes. Okay. So a couple things that give it away. Number one, you're laying down tiles which are copies of each side length. Those are multiples. Okay. Number two, you need to make a square, which means the two sides have to be the same. A multiple of two numbers that the same is a common multiple. Okay. And then there's one word in here that also tells me that it's a least common multiple. Yeah. Smallest. Yeah. So if you see a problem that says small, what's the smallest way that you can do this? And it's a least common multiple or greatest common factor question, you're looking for the least common multiple. If you see a question that says, what's the biggest way that you can do this? And it's that type of question, it's going to be a greatest common factor question. Okay? So essentially, if we draw the diagram, right, what we're doing is we're laying down copies of this rectangle. So if we did it this way, this right now is at 16. Another copy of 16 would be 32. Another copy of 16 would be 48. Okay. Well, now I know I'm going to have to go bigger than 40 on this side because I didn't hit 40 going this way. Another copy of 16, excuse me, would be, what is that, 64. And then another copy of 16 would be 80. Okay? Now, if I go down this way, now I'm laying down more copies of 40. 40 plus 40 is 80. So that would be the size of the square that I can make using these tiles. Okay? Now, if you recognize that this is a least common multiple problem, of course, you can look at the prime factorizations. Okay, so 16, it's actually 2 to the 4, right? It's a power of 2. So I'm just going to sort of skip over that in terms of the prime factorization. We know that's 16. 80, and by the way, if you know the prime factorizations, and you can do it in your head, you don't have to show me that process, it's 8 times 5, and 8 is 2 cubed. So I know it's going to be 2 cubed times 5, but let's just go through it. And the more you do this, the more you will be able to kind of start to do these. What did I do here? Oh, no, it's 16 times 5. It's 2 to the 4 times 5. My bad. Okay. Okay, so 16, no, 80. Wait, where did I make my mistake? I'm not prime factorizing 80. I'm prime factorizing 40. That's the size of the length of these rectangles. Okay, there we go. Did anyone know that I was making that mistake? Please, like, yell at me, throw something at me, whatever you need to do. I'm dealing with this, the 40, right? I want to find the LCM of 16 and 40. Okay, there we go. That's better. I was like, something's wrong there. 2 times 10, 2 times 5. There we go. Whew, all right. Okay, so if I'm looking for the LCM, I know I have to start with the entirety of the first one, which is 4 2's. Now I'm going to compare here. I need 3 2's and a 5. I've already got 3 2's in there, so I just need to add the 5, and that's 80. Okay. Questions with that one? No? All right. Now let's look at the sort of reverse type of question. What is the side length of the largest square that could be used to tile a rectangle that measures 16 by 40? So right now what we're doing is we're not using tiles and laying down copies of them. We've got this set rectangle, and we want to put squares, where the length and the width are the same, into this rectangle. We want to know what's the biggest square that we could use. Okay, what do we need to find between these two numbers here? Yeah, greatest common factor. Yeah. Now, that's not the only size square that would work. You could certainly do squares that are 1 by 1. Put teeny tiny little squares in, that works. You could do squares that are 2 by 2, that would work, but we want to know the largest one. Okay, so here we need to find the GCF. And again, many of you guys will know what this is, but looking at the prime factorizations, okay, we need to basically consider which are the primes that are shared. Okay, and they both have 1, 2. They both have a second 2. They both have a third 2. They do not both have a fourth 2. So that's it, 3 2s. Okay, so the GCF is 2 times 2 times 2, which is 8. Okay, and then if you lay it down this way, you can see 8 and 8 make 16. And if I have 5 going this way, right, 8 times 5 is 40. All right, any questions with that? Okay, so there are a couple of questions to do here, but I'm going to, these are very, very similar to the ones that I just did. So I'm going to stop with that now. And in the last 20 minutes or so, 25 minutes, if it's okay with you guys, I want to do a little recap on polynomials, because we're going to get into this next week. And I'm just going to dive straight in, assuming that you guys know what these are. So I'm actually going to add a page so that we can talk about this. You may want to just get out a blank page. I'm not sure. And let's talk a little bit about polynomials. Okay, so before we talk about what is a polynomial, I want to know what a monomial is. Okay, and what might be easiest here is if perhaps if you don't know the exact definition, one way to actually figure out the definition of something mathematically is to look at examples versus non-examples. Okay, does anyone have an example of a polynomial? Not a polynomial, sorry, a monomial. Yeah.
An example of a monomial is 5x or 9.
5x, say that again.
5x or another example is 9.
Okay, 5x, 9, anything else? Yep.
A monomial is a term that has like, or it's something that has like one term.
Okay.
Without being separated with signs or anything like
Okay.
that. So it could be like 5x to the power of 2 halves or something like that. Wouldn't that be a monomial?
5x to the power of 2 halves is a polynomial, but 5x to the power of 1 half is not.
Yeah.
Okay, so that's a polynomial. Okay, 3ab squared c, that's polynomial. No, not a polynomial, sorry, I keep saying that, monomial. Monomials technically are polynomials because polynomial is a general term. These are non-examples. Can anyone think of a non-example? And here I don't want an example that's actually a polynomial. I don't, like if it has 2 terms, let's not use those ones because that's not a good way of contrasting what's a monomial and what's not. Yeah?
X plus y plus z or something?
Okay, so x plus y plus c is a polynomial. So I don't want that type of non-example. I want a non-example of something where if you put it in a polynomial, that would also not be a polynomial. Okay? Yep.
Would like 16 minus 8 or something be right?
16 minus 8 equals 8, so that's a monomial.
Well, it's separated by a sign.
But you can simplify it too, right? So something like 2x plus 3x, that's actually a monomial because it's equal to 5x when simplified, okay? Here's something that is not a monomial, and if you put this into a polynomial, it would not be a polynomial either. Something like this. That is not a monomial. If you saw one of those in a quote-unquote polynomial, it would not be a polynomial. Okay? And with exponents that are whole numbers. Okay? Here's another example. That is not a monomial. Yes?
Maybe like irrational decimals.
Irrational decimals. Okay, so here's the deal. Good thought, but all numbers are actually monomials. So we're specifically considering not the numerical coefficient, but the piece that has the variable. Okay, this is not a monomial because as an exponent, it's written like this. So what can we tell? Okay, there's going to be variables in them, but the exponent on the variable cannot be fractional, and it cannot be negative. Okay, these are still algebraic expressions, but they're a different type of algebraic expression. Okay, this one's a radical expression. This one is a rational expression. Yeah?
Can a variable to the power of 0 be a monomial?
Yeah, so a variable to the power of 0, a to the 0, that is because it's equal to 1, which is a number. Yeah. Here's another one. That's not a monomial because the variable for a monomial must be in the base position. It cannot be in the exponent position. Okay? This is still an expression. It's called an exponential expression. Okay, so these are all non-examples. So let's put this together into a definition. A monomial is the product of numbers and variables. Numbers and or variables. Okay, so for example, this is the product of a 5 and an x. This is just a number. If you just have a number, it actually has a special name. It's called a constant, but it's still part of a monomial. Falls under that definition. This guy is the product of 5 times x times x times x. So I'm multiplying numbers and variables together, right? This one is the product of 3 times a times b times b times c. Those are all monomials, right? This one is just equal to 1, which is a number. And that's why an irrational number is in fact a monomial, because an irrational number is still a number. Okay? These ones are not. These are not. A polynomial. What is a polynomial? Yes?
Anything with more than 3 terms?
Okay, and well, not necessarily anything with more than 3 terms. All of these are polynomials. But can we haven't heard of the word term yet. So what does term mean? Can we create a definition of polynomial using what we know so far about monomials? Perhaps using that. Yeah?
Well, polynomial is just something I never know.
Okay. Yeah, anything else? Polynomial is the sum or difference of several monomials. One or more monomials. Okay? So if you add or subtract several of these together, you get a polynomial, or it falls under the category of polynomial. Polynomial is a general term, and so a monomial, although it has a special name, is called a polynomial as well. Now, I think why you said 3 or more terms is because if it has 1, 2, or 3 terms, it has a special name, but it is still a polynomial. So what is the name if there is 2 terms? Yeah.
Binomial?
And 3 terms? Trinomial. Beyond that, there's no special name, okay? Now, a term is another word for each monomial that you're adding and subtracting, right? So when we put these together in polynomials, each of those monomials that we add or subtract to create a polynomial is called a term in that polynomial, okay? So for example, if I did something like 3x plus y, this has 2 terms, okay? If I did something like this, okay, what if I did 4x minus x? How many terms in there? It's 1. Yeah, because this simplifies to 3x, okay? So this is actually 1 term. Okay, so how do we know if terms are like or unlike? Yep.
I just have like a question
Yeah.
about this. Do those definitions only apply once they're fully simplified? Like for example,
Correct. Yeah. Yeah. So a binomial is essentially any polynomial that has 2 different terms in it, right? 2 terms that are not like. Right? So if I did 5x minus x plus 3 minus 2x plus 7 plus 14x, that's a binomial because I only have 2 different terms. I've got an x term and I've got a number, which is called a constant. There's only 2 different terms in there. Yes, so you apply the definition once they're simplified, correct. Okay? You can simplify, talking about simplifying polynomials, polynomials can be simplified when they contain like terms. So let's discuss how do you tell if 2 terms are like. How do you know if 2 terms are like? Is x squared and 4x squared like? Yep. Is 5x cubed and 4x squared like? No. Is x squared y and y squared x like? No. So here's how you tell. Like terms must contain the exact same variables and the exact same exponent on each variable. On each, I should say, corresponding variable. Okay, so for example, 3x, whoops, I'm getting ahead of myself, 3x and negative 2x. Those are like, because they both have the variable x, and the exponent on the x is 1. Okay. Non-examples. Uh, 2x and 3y. Those are not like, because they have different variables. Okay. 2x cubed and negative 4x squared are not like. Okay, now why is the exponent so important? Because really what you're looking at is the expansion, right? This is x times x times x. This is just x times x. Those are not the same. Okay, what about this? What if I asked you AB and BA? Do you think those would be like or unlike? Yep. Like, yes. So AB and let's say 5BA. Those are like. Because remember, the operation that's going on between these two variables is multiplication. You can reorder multiplication, right? So this is A times B. This is B times A. You could reverse that and write it as A times B, and it's still the same thing. And they have the same variables, and the exponent on each variable is 1. Okay? What about A squared B and AB squared? No, right. So A squared B and AB squared. Those are unlike. You can tell from the expansion. This one is A times B. This one is A times B times B. Those are different. Okay, now, when you have like terms within a polynomial, they can be simplified, which means you add or subtract the coefficients. What's a coefficient, by the way? Let's talk about that. Coefficient versus variable versus constant. So let's say I have something like this. Negative 4a. What is the coefficient of that? Yes, correct. This is the coefficient. This is the variable. If a polynomial has a constant, what would that look like? Yeah.
A number that's not attached to a variable.
Correct. A constant is a number that's not attached to a variable. Okay? So for example, if I have 2x minus 7, what is the constant? What's the constant there? Yeah. Good. It's negative 7. Okay, so one important thing about coefficients and constants is that they have signs. Okay, so that's the constant. Okay, when we are simplifying a polynomial, we've already seen, I believe, a little bit of this. Where did we see it? Oh, when we were solving equations, right? Where you can collect like terms, which just means essentially add or subtract those coefficients together of each unique term. So for example, if I asked you to simplify 4x squared minus 5x plus 2x squared minus 3 plus 7x minus 5 plus x squared. Okay. How many different terms do I have in this polynomial? How many unique terms are there? Yeah, there's 3. Okay, so what are the unique terms? What different terms do I have? Yeah, you have an x squared term. So if you have more than one x squared terms, those can be combined. So I'm going to underline all of those in one color. Okay, what's another term that I have in this polynomial? Yeah, an x term, correct. So we'll do that in a different color. And then what's another term that I have? Yes? The constants, correct. Yep. So the constants are here. Okay, so when you are combining like terms, you want to essentially add or subtract the coefficients, right? So for the x squared term, I've got 4x squared plus 2x squared plus x squared. What's the coefficient of this last one, of the x squared term? Yeah, it's 1, Correct, because you could write it as 1x squared. Coefficient is essentially how many of this term do I have? If you're adding x squared, you have one of them, 1x squared. Okay? So for the x squared terms, I have, you know, and a lot of you guys don't need to do this. You can do this in your head, but you have 4x squared plus 2x squared plus x squared. And remember, that's like 1x squared. That's 7x squareds. Okay. For the x term, I have negative 5x plus 7x. How does that simplify? 2x, correct. And then finally, for the coefficient, I have negative 3 minus 5. And that is negative 8. So all together, this becomes 7x squared plus 2x minus 8. Would it also be, could I also write it as 2x plus 7x squared minus 8? Would that be the same thing? Yeah, totally, right? Because like 2 plus 5 is the same as 5 plus 2. What about if I wrote it as negative 8 plus 2x plus 7x squared? Would that be the same? Yeah, so you can reorder the terms as long as the sign of the coefficient in front is maintained. So if I said it was 8 plus 2x squared minus 7x squared, that would not be true. Because if it was minus 7x squared, now the coefficient is not 7, it's negative 7. Okay? Typically, though, when we are simplifying, we tend to write the terms in descending powers of x or y or whatever variable you're looking at, just because it helps to keep it organized. And when we try and factor something like this, that's going to be helpful. Okay, so we're going to take something like this in this unit and break it up into the two factors that multiply to that particular polynomial. Okay, now the last thing I want to talk about is multiplying monomials together and dividing monomials, right? So some of you guys actually may have done this last year where you're taking a monomial and multiplying it by a binomial or a trinomial, or vice versa, or dividing, right? But let's just talk about multiplying and dividing monomials, okay? And really what this ties into is our exponent laws, right? So if I'm looking at multiplying or dividing monomials, right? So if I do like 2x squared y times negative 5x y cubed, right? This is the multiplication of two monomials. Well, I use my exponent laws to simplify, right? So here it would be the product law. In terms of the coefficients, I'm going to multiply these two together. So it's 2 times negative 5, which is negative 10. And then x squared times x is x cubed. Y times y cubed is y to the 4. Okay. When I'm dividing, let's say I have 10a to the 4b cubed over 4a cubed b. How would you do that? Which, in terms of our last unit, yeah?
Divide 10 by 4.
Okay, so divide 10 by 4, and that is 10 divided by 4. No, it's not. 2.5, right? I think? Because it's 5 over 2. So you can either, the 10 over 4, because 10 over 4 terminates as a decimal, you could write it as 2.5, or you could write it as 5 over 2. Either one is fine, okay? And then what about this piece, the a to the 4 over a cubed? Yeah? A, because you're using your quotient rule, right? So subtract. So 4 minus 3 is 1, so it's a. And then b cubed over b. Yeah?
Would just be b to the 2.
B squared.
You're getting rid of one b.
Correct.
Top to the bottom.
Yeah, good. Okay, now did you guys last year see anything that looks like this? Now I'm taking a monomial and I'm multiplying it by a binomial. Have you guys seen that before? Raise your hand if you've done that. Yeah? Okay. Cool. So how do we do this? Yeah.
Multiply the outside term by each inside.
Yes. So this is called distribution, right? We distribute the multiplication of 3x to all terms inside the bracket, right? So this becomes 3x times 2x is what? 6x squared. And then 3x times 5? 15x. Now I want to just bring up something that I started with today, and then I'm going to stop for today, and that's this. Okay, let's say I'm doing that. I can also look at it this way. And distribute. So 3 times 10 is 30. 3 times 7 is 21, which is 51. Okay, using an area model, I draw a rectangle that's 3 by 17. Here's 3. I'm going to split the 17 up into 10 and 7. Here's my 30. Here's my 21. And those add to 51. Okay? Now, using the algebraic example, 3x times, what was it, 2x plus 5? Oh, shoot, I forgot. Okay. So we're going to go out this way. Okay, we're going to go out this way and that way. Can I get someone to close the door? Thank you. All right, let's go this way.